Okay, hey everyone, this is Connor Mead with the Calculation Center. Here's our third video on solving systems of linear equations. Hopefully you've seen the first two. The first one we dealt with solving a system of linear equations which had a single solution. The second video we solved a system of equations with no solutions. And in this one we're going to do the third type of possible system of linear equation, a system of equations with infinite solutions. This is probably the most difficult of the three types of systems to solve, so hopefully you're familiar with how to solve the first two already, because we're going to be building up off of that idea. Okay. The basic principle for all three of these things, however, is basically the same. We're going to try and do row operations using the pivot algorithm to try and reduce this left-hand side to the identity matrix, which is the matrix with just zeros everywhere, except for along the diagonal where it's got ones. Okay. But let's remember what we do. We put a pivot around our top left entry, and we use that pivot to turn everything below it into 0. So we're going to send, for example, row 2 to row 2 minus 4 row 1, right? Because we have a 4 here. So if we subtract off 4 copies of this one, we'll turn it into 0. And row 3 goes to row 3 minus 3 row 1. Okay? So the first row obviously doesn't change because we're not doing anything to it. We need to be careful with the rest of them. These both become zeros by design. And now let's look at what we have left. So we're subtracting off 4 copies of minus 1, that's adding 4. So we've got minus 2 plus 4 is 2. And 6 minus 4 copies of 1 gets us a 2. And we're subtracting off 3 copies of row 1 for row 3. Oh, we'll better do this side as well, actually. This would be minus 2, because we're 6 minus 4 times 2. Here, however, we'll get 0. This will be 4, right? 7 minus 3 times 1 is 4. And now, well, let's look what we get here. We get 2 minus 3 times 2, that's minus 4. Okay, so you might see something similar happening to what was happening last time. In our last video, something went wrong basically because we ended up with a row of zeros at the bottom equal to a non-constant number. However, what we see is going to happen here. Well, let's continue with the algorithm just to make sure we know what's going on. We're going to use everything inside this pivot box to turn everything below it into zeros. We get 1 minus 1, 1, 0, 2, 2, 2, minus 2. Basically, we're not going to change anything, so I just said I'd write all this out. We're not going to change anything in the first 2 rows, I should say. And lastly, let's send row 3 to row 3 minus 2 row 2 in order to turn this 4 here into a 0. So what we get here is 0. 4 minus 2 times 2 is 0. 4 minus 2 times 2 is 0. Minus 4 minus 2 times minus 2, that's minus 4 plus 4, so that'll be 0 as well. So compared to what happened last time, in the last video. In the last video, we had something like 0, 0, 0, and then 7 to the right here. But in this case, we have 0, 0, 0, 0. So this last equation isn't actually a contradiction. If we look at these equations, we get this first equation is x minus y plus z is equal to 2. The second equation is 2y plus 2z is equal to minus 2. And this last line says 0x plus 0y plus 0z is equal to 0. And maybe we could say there's a 0x in this equation as well. But last time, this equation was a contradiction, so we concluded that the system of equations must have had no solutions, because there was no x, y, and z that you could put into it to get 7 on the other side, or whatever it was. But in this case, any x and y and z would solve this equation. No matter what we choose for x, y, and z, we solve the equation. So basically, this last equation didn't actually give us any information. So how do we solve from here? Okay, let's, well, we can't put any pivot in the bottom row, because they're all zeros, and you can't put a pivot around a 0. So what we have to do here is basically continue on as if we've already finished with our Gaussian elimination and proceed with back substitution, okay? So instead, we're going to assume we've put in all the pivots we can going this way, because we have, and we're going to start substituting back in the other direction. What this means is we basically want to turn this thing into a 0, and then we'll be done, because everything above and below our pivots will be 0. And then I'll show you how we can get our solutions from that. Okay, so let's send row 1 to row 1 plus row 2 over 2. So we'll get, well, let's fill in everything. We still have our row of zeros at the bottom. We haven't changed that. Let's leave this like this for now, I guess. And what will happen here, this will become a 0, because we're dividing the second row by 2 and adding it to the first. So this first entry will cancel, this second entry will become 2, and this first entry here will become 1. Okay, because we're adding on 1 and subtracting off 1. I'm sorry, did I get this right? Yes, that looks fine. So we got our pivots. Now at this point, I would say we've done as much as we can in this augmented matrix equation, so I would suggest we turn it back to a system of linear equations to see what we figured out. Okay, so we know that x plus 2z is equal to 1, and 2y plus 2z is equal to minus 2. Now, what we should notice here is that although we've got 2 equations, we've got 3 variables, okay? And what that generally means is that we're going to have infinite solutions. So what that means is we should write our solutions for x and y in terms of z, okay? So we notice that x is equal to 1 minus 2z, y is equal to minus 2, well actually 2y, well let's just divide across by 2. This can be broken down into y is equal to minus 1 minus z. And this is basically classifying all our possible solutions. So what this system is, and well, I guess we have a line saying down here z is equal to z. What this means is all of our solutions, all solutions are of this form. Okay, so what that means is if I pick a number z, I can find a solution by setting y equal to minus 1 minus z and choosing x equal 1 minus 2z. So our solutions look like, i.e., they look like, if we were to write them as a vector, for example, they look like 1 minus 2z, minus 1 minus z for any z in R. Well, R could also probably be replaced with C here and things like that, but let's just assume we're dealing with real numbers here for simplicity's sake. But this is all solutions. Just for so this is basically your answer to this question. These are all possible solutions. But just for some examples, e.g., if z is equal to 1, we'll notice that minus 1, minus 2, 1 is a solution. If z is equal to minus 1, we'll get 3, 0, minus 1 is a solution. And if z is equal to like pi, then 1 minus 2 pi is a solution, minus 1 minus pi is a solution, and pi, and the third component is pi. So remember that our solutions are coming in triples because we have to have a value for x, y, and z, and this classifies all possible of those such triples. Okay? This was our last video on solving systems of linear equations, so hopefully they were helpful. But for now, we're finished with this section.